I'm Amir, and my advisor is Dr. Mubarak Shah. So, georeference data has a great impact on our lives these days. So there are lots of applications they are used in. So geographical data organization is one of the things that we have seen. Like we have seen services like Panoramio or Google Earth, and also they have been used for other applications like building 3D models of cities. So, however, there are many images and videos that are not geotagged these days. So that's why, because there has been a lot of interest in developing automatic localization methods in computer vision. So this problem was traditionally attempted for overhead imagery, where the picture would be coming from a plane or satellite, and the problem would be to geo-register it on a DOQ and get the geolocalization information. However, during the past decade, ground-level data has been dominating. So structured databases like a Street View or unstructured data like user-shared images are the two main resources of ground-level data. So these ground-level data render the conventional geo-registration techniques unuseful. That's mainly because they violate their assumptions like planarity of the scene and occlusion and so on. So, however, they empower adopting a new approach based on image matching for geolocalization. The challenges faced when we want to do geolocalization using image matching is, like, first, there's a large amount of data that we need to process. And also, there is ambiguity of and excessive similarity of man-made structures, which makes localization, visual geolocalization difficult. And also, there is undesirable photography effects. Therefore, the goal is to make the system fast, scalable to larger scale, relatively accurate, comparable to GPS possibly, and applicable to various images. The existing methods to visual geolocalization can be roughly categorized into three categories. So the first category is for coarse geolocalization, extracting geographical information, like image to GPS is probably the most notable work in this area, which is mostly focused on saying where this picture, in what continent it was taken, or whether it shows a desert or coast. Another set of approaches are based on a structure for motion and people geometry techniques, which are based on establishing a geometric relationship between the query and the reference data. Also in robotics, this problem has been attempted several times by several methods. SLAM and FOBMAP are probably notable work in this area. What we are going to talk about is fine geolocalization using image matching, which doesn't entirely fit in any of these three categories. So in this dissertation, we address three fundamental questions in geospatial analysis of ground-level imagery. So first, we'll talk about how we can geolocate images and videos if they're not coming with a geotag. If they're coming with a geotag, how we can refine the geolocation. And once the geolocation is known, how we can utilize it to better understand the content of the image and so. So the outline of the presentation is, first we'll talk about image geolocalization, we'll talk about location feature matching and geospatial pruning, and then multiple nearest neighbor matching. Then I'll show video localization and trajectory extraction, robust refinement of geolocation, and finally location-aware image understanding for business recognition. So the first part is image matching using local features and geospatial pruning, which was presented in ECCV 2010. So as I talked about, the problem is, given an image, no metadata, we want to find where the image was captured. And we want to make it accurate and fast. So for the reference data, we use Google Street View in this work, and the test data is always user-shared images, typically from Panoramio, Picasso, Flickr. So this slide shows the distribution of our reference data from Pittsburgh and the distribution of our query images from the same area. Similarly, distribution of reference data for Orlando and query images. So to pre-process the reference data that we have, given one of these Street View images, we extract SIFT points from them and SIFT descriptors, and we also aggregate these descriptors from all of the Street View images that we have, and we organize them in a k-means tree, along with the longitude and latitude of the image that they were coming from. So all the data goes to the k-means tree. Then when we want to geolocalize a query image, first, given the query image, we extract, again, SIFT points from it, And then we'll go to the reference tree for each of these query SIFT points. We'll find the first nearest neighbor, and that is coming with a longitude and latitude. So we assign the longitude and latitude of the nearest neighbors to as the location of that particular local feature. And we do that for all the local features that we have. So if we show the distribution that they actually form, it looks something like this. So x and y axis show the location, and vertical axis shows the number of votes. So we can look at it as a probability. So this location so far is where it's more likely for the image to be captured at. But obviously some of these correspondences that we found are incorrect. So we want to develop methods for removing these correspondences and prune them. So the normal approach is to examine the discrimination between nearest neighbors, typically between first and second nearest neighbor. If the first and second nearest neighbor are very similar to each other, it's not a good choice. If first is much better than second, it's usually concluded that that's a good one. But this has a problem in urban areas, so we developed geospatial pruning, which determines the verification SIFT point adaptively. And for that, it incorporates the geospatial distance along with the descriptor distance. So the way it works is that instead of comparing the discrimination of first nearest neighbor with respect to the second one, it does it between first and the one which does not belong to the geographically neighboring area. And by doing that, it makes sure that the repeated architectural features or overlapping seen in various images is not contributing to the fact that like multiple nearest neighbors are being proposed for one query feature. So by doing that, like if we do not use this approach, if you just go with the basic first and second nearest neighbor, this is what you get. The yellow ones are the ones which survive the pruning. And as you see, most of the features which are meaningful for geolocalization purposes are removed. So first and second, because of the problems that we talk about, over prunes. But if you go with our method, geospatial pruning preserves most of the geographically meaningful features. And as the last step, after doing a smoothing by two-dimensional Gaussian, we pick the location which has the highest likelihood as the location of the query image. So in this particular case, here's the query. This is the match that we found. And the difference between them in terms of the geospatial error is about 17.8 meters, which is pretty good in the scale of whole town, which is miles wide. So the largest scale results using this method is shown in these plots. So this is the distance threshold shown on the x-axis, and y-axis shows the percentage of query images localized within that. So Schindler, Brown, and Zelinsky baseline gets 35% of the test set localized within 250 meters. The same number for our method is about 75%. And the difference between the green and blue curve is what you would expect to get if you did not use the geospatial pruning. And as you see, proper pruning of these correspondences makes a big difference in the overall results. So some qualitative results. In 68% of the cases, the algorithm found the very best match for each of the query images that exist in a data set. And as you see, the error is very small, 9 meters, 6 meters, and so. In 13% of the cases, a meaningful match was found, but not necessarily the best one. And that's because, like for instance, this building is the same as the one here, but this found reference image is not necessarily the very best one for this query image. And in 18% of the cases, the algorithm totally failed to find the right location, anything in common. And that's basically, for instance, in this image, like these windows and like rectangular shaped structures are the same, very similar to these ones in terms of local features. So that's why the algorithm gets confused. And we'll talk about that actually in the next piece, how we can disambiguate local features. So with that, we move to the next chapter, which is on multiple nearest neighbor feature matching, which is, has been accepted for PAMI 2014. So local features have a serious ambiguity. For instance, these two patches, if you look at them, they look very similar to each other. But if you look at the whole image, they're actually entirely very different. So such confusions are very common in large databases and challenging data sets, so especially in urban area. We want to disambiguate the local features by supplying them with global features. So by global features, I mean like global color histogram of the image, gist, or even like non-visual features like geotags. Another issue that local features have is that the first nearest neighbor is not necessarily the right one. Local features are usually used with nearest neighbor classifier for establishing the correspondences. But if you, for instance, look at the first nearest neighbor returned by nearest neighbor classifier for the query features of this image, and also look at the second, third, and so forth nearest neighbors, you'll see that the correct nearest neighbors, meaning that the ones which are actually coming from the right image, are not necessarily the first one. Third, second, first, and so on. So that's again happening because of the small scope of the local features. So we want to develop an algorithm which is invariant with respect to the rank of the nearest neighbor as long as it shows up among the top matches. And we do that using GMCP. So what GMCP, or generalized minimum click problem, is in graph theory is that you're given a graph, and the nodes in the graph are clustered into disjoint groups. And the GMCP is then defined as selecting one node from each cluster in a way that the cost of the click that they form is minimized. So, and the cost of the click is defined as the summation of the edges there. So we want to solve our feature matching problem using GMCP. So to form the input to the GMCP graph, we have these nearest neighbors nominated for one query feature. Each of them is represented by a node in the graph, and we put them in one cluster. So one cluster represents one query feature. And we do it for the second query feature, and so on and so forth for all the query features. So each cluster represents one query feature, and the nodes therein represent the basically nearest neighbors. Then you form the k-partite complete graph. So in the k-partite complete graph that we have, there are edge costs and node costs. So edge costs capture the similarity between global features. So one edge is between two nodes, and two nodes are basically nearest neighbors of local features. So the edge weight captures how similar the global features of the images those two local features are coming from. And also we have the node cost, and node cost captures the similarity between the local features, and which is defined as the distance between the local feature, like SIFT in this case, SIFT in the query image, and the nearest neighbor. So by solving GMCP, one node from each cluster is selected in a way that both local and global features are incorporated. So this is the cost of the click actually. And the cost of the click is defined as summation of the edges as well as the summation of the nodes there. So as I explained, the local features are represented in the nodes, and the global features are in the edges. So by finding the click, we are the minimum click, which minimizes distance. We are finding actually the set of nearest neighbors which are in maximal agreement between local and global features. So, however, there is an issue that we need to solve here. So, to better understand it, let's look at this sample. This is the query image, and the nearest neighbors are shown in the two-dimensional global feature space. Each node represents one nearest neighbor. And the red nodes here show the inliers. It means the nearest neighbors which are coming actually from a matching image to the query feature. So in this case, as you see, most of these all of them form a tight cluster in the global feature space. That's because the global features of all these matching images is similar. However, in practice, we often observe cases like this, that the matching images to the query image are actually form disjoint clusters, and that's because the global features of a subset of the matching images is very different from the global features of another subset of the matching images. And this is problematic for basic GMCP. That's because the edges that would be required to connect these two inlier sets would induce a high cost and consequently stop GMCP from working properly. And this kind of disjoint clusters happen because of variation in illumination or camera type or viewpoint, anything which could cause the global features to be different while the images are showing the same thing. So our solution is to robustify the distance function which we use for global features. So instead of using the basic Euclidean distance, we use this distance function d. So if you plot this, the relationship between Euclidean distance and distance function d is shown in this curve. So intuitively, it has the property of boosting the short distances, or not touching them actually, and damping the large ones. So again, intuitively what it does is that it allows GMCP to concentrate on inter-cluster distances, not intra-cluster distances. And that's because once you get away from a certain point of the inlier set, it doesn't matter how far you go. The distance, the cost that it induces is always fixed. So that's why the inter-cluster similarity and tightness matters much more than distance within disjoint groups. So it doesn't matter like how many disjoint groups you have. They're actually going to be selected eventually. So this distance function came from GRB of kernel. And actually using this distance function can be viewed as transforming the global feature space into a projected feature space and measuring the distances there. So the reason we are saying that is that if you look at the definition of GRB of kernel, this is the kernel K, and we can get the distance between two feature points in the projected feature space using this equation if the transformation is done by kernel K. By plugging the definition of GRB of kernel into this equation, you'll get distance D. That's why measuring the distance using this distance function is actually going to another, projecting the global features into another infinite dimensional feature, measuring it there. So the difference that it makes in practice is, in this case, for instance, there are 3 disjoint inlier groups. Without robustification, GMCP takes one of them and just scatters the rest of the selections around that inlier set. With robustified distance, it actually is able to capture all 3 of the inlier sets. Another case, 2 disjoint clusters. Without robustification, it fails. With robustification, it's able to capture both, while here, only one of them is taken. So to solve GMCP is an NP-hard problem, and which requires an approximation for solving it. And we use local search for solving GMCP, which is like suboptimal method. And it's typically useful for computationally hard combinatorial problems. It has been applied to several similar problems. And it's a meta-heuristic method. So like in the most basic form, what local search does is that you have one initial solution, either randomly generated or with some prior knowledge. You have one initial solution. You generate a set of neighboring solutions, and you find the best neighboring solution to the current solution that you have. And you keep doing this. You select actually the best neighboring solution, and you move to that one. And you keep doing this process in the hope of descending to the minimum. And neighboring solutions are actually defined as 2 solutions which are identical except in one element. Neighboring solutions of size 1. So for instance, in the context of GMCP, this is one feasible solution to GMCP represented by this vector, which shows the indexes of the nodes. This is another feasible solution to GMCP, which is represented by another vector with a difference that the first elements are different. These 2 solutions are identical except for the selected node in these 2 clusters. So these are basically neighboring solutions. So a little bit more complicated version of our solver got 79% of optimality in our geolocalization GMCP instances. We found the optimal solution using exhaustive search, which took a long time, but we wanted to compare it to actually what local search gives us. And in 79%, they were identical. And using local search and MATLAB octa-core 2.4 gigahertz, it typically takes less than 1 second in a parallel code to solve one instance of GMCP. So to see some overall results, this curve shows the results of the method that I explained earlier, and the green curve shows the performance of chances. As you see, it's very, very small. That's because the area that you're looking at is huge. This is the result that Schindler, Brown, and Zalewski's method get. This is slightly worse than the other method. And this is what GMCP gets, which is like 7 to 10% point-to-point different from the next best baseline. And also there are some other baselines. For instance, if you do early fusion of local and global features, and also if you randomly select one of the nearest neighbors. So these are basically the results that each one get, and GMCP outperforms all of them. So these two curves show the difference that robustification makes. Solid curve is with robustification, dashed curve without robustification, which shows robustification makes a difference in the overall geolocation results. And GMST is generalized minimum spanning tree, and that's actually a dual of GMCP with difference that instead of having a tree, having a click, it has a tree. And the reason it's dual is that it's actually a linkage-based mechanism which the tree can be looked at as. And so it doesn't require the robustification for dealing with the disjoint clusters, but the robustification doesn't make any improvement in it too. So the conclusion is that GMCP with the robust distance function does the best in our formulation. And also we have alternatives for robust distance function to show that our method actually makes a difference in the end. These are the alternative methods like Hubbard loss, linear loss, squared loss, and these are the geolocalization results that each of these methods yield. And as you see again, GRBF kernel does the best, and squared loss, which is actually the opposite of what GRBF does, does the worst, which shows the intuition that we had for robustification actually is meaningful. So with that, we move to the next chapter for video geolocalization, which was presented in CVPR 2012. So far we talked about images, but now you want to see what you can do with videos. So what we are trying to do is, given a video, like for instance a YouTube clip, we want to be able to tell where exactly each part of the video was recorded, and in the end be able to capture its geospatial trajectory. So we start with segmenting, geolocalizing each segment of the video, and then Bayesian filtering, and then an offline MST reconstruction. I'll explain each one in more detail, but the first step is video segmentation, video segment localization. So we divide the video into smaller segments of 2 to 5 seconds uniformly, and we geolocalize each frame in the segment using the image localization method that I explained earlier, and we put the distribution function that each one gives and put them together, and we make one final PDF which represents the location of the segment. The next step is to Bayesian filtering. So Bayesian filtering is expected to enforce a temporal consistency. So we have the PDF that we get for the current segment of the video, and which we look at as likelihood. And we have the PDF that we got after applying Bayesian filtering to the previous segment of the video. And we apply a motion model to it, and we get the prediction for the location of the current segment of the video. So we multiply likelihood and prediction in the Bayesian formulation. We get one final PDF for the whole segment, which is temporally consistent over the course of the whole video, and also the current segment's information. And the last step is to do MST-based reconstruction. So if you look at the output of Bayesian filtering, for instance, in this case, the purple trajectory is the output. It does a good job in going down to a small block, but still there are inconsistencies in there. There's back and forth movement on a smoothness, and that's because the motion model that is assumed in the Bayesian filtering is violated. And we observe that in YouTube clips and like videos that people capture, they tend to walk in a stochastic way. They don't follow any particular motion model. So that's why Bayesian filtering will never be able to return an ideal trajectory. So for solving that problem, we propose this MST-based reconstruction technique. So we look at the output of Bayesian filtering, the location of each segment as a node in a graph, and that's coming with x, y, and t. X, y is the location, and t is the time. So it's coming with a three-dimensional feature. So we grow a minimum spanning tree in that three-dimensional feature, which is shown here, and also the corresponding track is shown on the map down there. So then if you look at this tree carefully, there are some nodes which have a degree higher than 2. Degree higher than 2 in the MST space, it means there's a back and forth movement. There is something which is not consistent in this space-time. So for instance, if you look at these nodes which are marked with the big orange node, these are the nodes which have a degree higher than 2. And if you look at the corresponding node in the Bayesian trajectory, there's always, they correspond to some problem. Like there is one basically big turn here, there's a small turn here which is corresponding to that, and so on and so forth. So for each of those nodes, we actually go and preserve the 2 biggest branches which is connected to the body of the graph, and we discard the rest of the nodes. And if we do that process for all of the nodes with a degree higher than 2, the red trajectory is what you get as the output. And as you see, it's much more similar to the green trajectory as compared to what Bayesian filtering gave you. And this algorithm actually does what I just explained. Looking at each node, finding a degree higher than 2, and removing the branches. So to see how it actually works in practice, for instance, this is the trajectory of a YouTube clip before reconstruction, and this is after reconstruction. As you see, like this part, which is quite meaningless, is actually taken out. Another example is shown here, which we saw actually earlier, and more examples. As you see, like in different scenarios, it's working constantly well. It doesn't really matter. It doesn't have anything, any notion of the shape of the trajectory, then that's because it's a non-parametric method for reconstruction. So we did our experiments using 45 videos from YouTube, and or recorded by random users from Orlando downtown and Pittsburgh downtown, and the average length of the video is about 1.5 minutes. So this is an example. As the video goes forward, you see the blue dots are being added to the map, and that shows the current segment of the video, and the green trajectory shows the ground truth. And notice that there's a lot of like jittering and shake and abrupt changes in the direction, and well, it shows that like any method which would try to establish a relationship between consecutive frames is not going to work well, like such as structure from motion and so on. So as we approach the end of the video, actually, which is close here, we'll then apply the MST-based reconstruction. And this is the results of frame-by-frame geolocalization, which is pretty noisy. And this is the results of MST-based reconstruction, as we saw before, of the Bayesian filtering, as we saw before, and this is the results of MST-based reconstruction. So we have many of these videos that we could look at. In terms of quantitative results, so the point-to-point error between ground truth trajectory and the frame-by-frame is 268 meters. And after applying Bayesian filtering, it goes down to 10.5 meters. And again, after applying MST-based reconstruction, it goes to 9.9 meters. But besides the improvement the MST-based reconstruction makes in terms of the number, it makes the output trajectory much more visually pleasing and smooth and closer to the ground truth. So with that, we move to the chapter 6, robust refinement of geolocations using random walks with an adaptive damping factor, which has been accepted for CVPR 2014. So, so far we talked about how we can automatically geolocalize the data. But what if the image is already geotagged? It's coming with a geotag. And this is particularly important that now most of the images are being geotagged at the time of collection. There's an internal GPS, there's WPS, Wi-Fi positioning system, there's cell tower signal, and so on. So most of the images are coming with some sort of the geotag. But the problem is that they are inaccurate. So it's a known issue in crowdsourcing that the crowdsourced geotags have a lot of inaccuracy in them. So that's what we are going to focus and we are going to solve. So to see this better, look at, for instance, these 100 user-shared images from Pittsburgh. So each blue node shows the user tags for one image, and the red node shows the right location, actually the correct location for that particular one. And as you see, a wide range of error can be observed here. Like some of them have short arrows, like few meters or few tens of meters, and some of them have like hundreds of meters of error. So to study the statistical properties of actually the noise in the geotags, we did an experiment on 8,000 user-shared images from Pittsburgh area. So we found that about 75% of the user-shared images actually have an accurate tag. And by accurate, they mean like the error is less than 30 meters, which is the nominal error of GPS devices, typically between 15 to 30 meters. But the ones which have a larger error, they actually show this distribution shown in the right, which is a near Gaussian distribution with a peak at about 415 meters, which is pretty significant, and that's what we're going to focus and solve in this part. So formally, the problem is, given a data set of images which are geotagged, this data set has a subset of geotags unknown subset, which is inaccurate. So we want to identify that subset and refine the location to the right one, to the right location. And we do self-refinement. We don't need a street view or any uncontaminated data to be supplied. We refine the data set using the rest of the images and aggregation methods in here. And also it's a robust method. It means like there's internal mechanism for dealing with outliers here. So overall, what the method does, there's a query image, there's a user's tag, and there is a first we do matching between the query image and the rest of the images in the dataset to find the visually most similar images, and we retrieve all of them. And then we form triplets and generate the estimation based on triplet. We generate a large number of these triplets, and then we do random walk on these triplets to be triplet estimations to be able to identify the inlier set. And finally, we do weighted mean and the relevancy score that the random walk returns to be able to find the refined GPS tag. So I'll explain it in more details. So as I said, the first step is to do image massing. So there's query image. We go to the data set and find the most similar images from the data. And for instance, the ones shown down there. Then we form triplets. The triplet is formed using the query image and two of the retrieved images. And then we find correspondences which are in common between these three images. And then using trifocal tensor and epipolar geometry and structure for motion techniques, we find the relative location of these three, like the relative location of the query image with respect to the first retrieved image and second retrieved image. And since these two images are coming with the geotag, they're coming from the data, from the reference data, from the data set that we have, we can actually estimate the location of the query with respect to them, given their global position and the relative location that the trifocal tensor gives us. So that actually gives us one estimation for the location of the query, which we actually show here in the east-north up metric system. Then we move on to the next feasible. Another pair plus the query image, it actually gives another location. And we do that for all the possible triplets that we can form. And using that, we get a large number of estimations for the location of the query. And however, as we know, like the unknown subset of the data set has inaccurate tag. So we expect a considerable subset of these estimations to be incorrect. So we want to now identify this uncropped estimations and use them for actually finding the right location of the query image. So we do that using random walk. Random walk is a special case of Markov chain with the reversibility property, which is essential for the concept of walks. And so in high level, it can be viewed as a diffusion method, like for diffusing the relevancy score of a node according to a predefined transition function. For instance, let's look at this graph. There are some nodes which are strongly connected and in the dense part of the graph, and there are some nodes which are remote and isolated. So imagine one person wants to walk on the nodes of this graph from one node to another. And this, the probability of moving from one node to another is predefined. So you would expect after a sufficiently large number of walks, the nodes which are actually highly consistent with each other would be visited more often, and the nodes which are actually not that consistent, they would be visited less often. So then if you define a relevance measure based on the number of times that each node is visited, you would expect the the set of consistent nodes to stand out, and the set of outliers which are not consistent with most of the majority, they would go away. So that's basically what is shown here. So we want to use this, the same concept for actually doing the refinement of geotags. So we define the transition probability between two nodes based on their GPS distance using this, using this normalized exponential. So what it does is basically using an exponential, and by normalizing it, it assigns a higher probability to the nodes which are closer in terms of the GPS distance, in terms of their estimations, because that means they are more likely to correspond. They're more consistent to each other. And it assigns, for instance, like these nodes would have a high transition probability. And the nodes which are far away from each other, they would have a low transition probability because they are not consistent to each other. So then again, like I said, given the estimations, given this transitional probability, and the random walk formulation, which actually has one Markov chain term as well as a damping factor, which we'll talk about later, it updates the relevancy scores of each node to find a consistent set. So if you do that, this is what you get as the output. So the relevancy score is color-coded. As you see, the set of the nodes which are highly consistent to each other gain a higher relevancy scores, and the ones which are removed and isolated and they're not consistent, they get a low relevancy score. So given the relevancy scores, we want now to devise the final location for the query image. We do that using a weighted mean, using the stationary probability that random walk actually converged to. So for each of GI is the location of the GPS location of each of those estimations, and X pi is the stationary probability, the relevancy score that the random walk converged to. And we do the weighted mean using that to find the final location. And it's shown actually with the blue marker here. So the blue marker is, as you see, is much closer to the ground truth as compared to the purple marker, which is actually the user's tag. It shows that our method has significantly improved the error. By the way, we use the initial location of the query image as one of the nodes in this random walk. So that is incorporated as well. Another thing that we need to incorporate in the random walk formulation is the non-uniform distribution of user-shared images for different locations. So user-shared images have a very, very non-uniform distribution for different areas. That's because people find different things attractive for photography. So some areas are quite sparse, some areas are quite dense. So that acts as a bias in generating estimation. That's because you have more estimations for particular locations, obviously more retrieved images, and more estimations will be generated based on them. So that will act as a bias and makes it a problem there. So we extract the density map, which actually captures the density of the different locations, and then we want to feed that in random walk as a prior, so the bias that the non-uniform distribution causes cancels out. So we'll talk about the damping factor in more detail, but in general, constant damping factor, which is the basic way of putting damping factor, random walk has an issue, and that's being prone to noise in the input. And the reason is that like for instance, let's look at the damping factor in random walk. So what basically it means is that there is a Markov chain term and there is a damping factor term. So the output relevancy score always has a fixed share of the initial score. So now if the initial score is actually contaminated or the estimations are contaminated, a fixed share of them is always going to show up in the output, which violates the robustness assumption. And because in any robust method, the output can't be directly related to input. There has to be some filter halfway through. So the way we solve this problem is by proposing an adaptive damping factor for random walk. So this is actually the formulation of random walk after plugging the adaptive damping factor, which becomes like looks pretty complicated. But let's look at the damping factor term to better understand what it does. So what it really does is it makes the contribution of initial score of one node dependent on the relevance, so far best relevance score that was found. So if the Markov chain term found one particular node to be inconsistent with the rest of the nodes, then it would have a low relevance score, and consequently after multiplying to the initial score, it would have a low cost, and therefore it wouldn't have any share in the output. So by this trick we are making the damping factor adaptive, which conforms to the level of noise for each node. And also the first term then is got based on the constraint that the linear mixture of these two terms has to be always 1, the summation. So 1 minus term 2 is a term 1. So we'll see how it actually makes a difference in results. We did our experiments using 18,000 user-shared images, and from San Francisco, Pittsburgh, and Washington, D.C. And test set was 500 randomly generated, which we generated the ground truth for. So this distribution shows the distribution of error in the input and the output. The input is shown in blue and the output is red. So as you see, as compared to the input, the distribution of error in the output is skewed to the left, which actually shows that the error in the output is significantly reduced. And this is the scatter plot from which these two distributions were drawn. So each node represents one image, and x-axis shows the output error, and y-axis shows the input. As you see, most of the nodes are above the main diagonal, which means our method improved the overall, case-by-case error as well. So the mean is 88 meters in the input, and the output after refinement is about 20 meters. So to evaluate our adaptive damping factor, so for alpha 0.6, these two distributions show the probability of distribution of error if we use adaptive damping factor and if we use constant damping factor. So adaptive damping factor is shown in red and constant damping factor is shown in green. And as I see again, adaptive damping factor is much skewed to the left as compared to the other one. And again, this is the same distribution from which that is drawn. So 276 as compared to 63. This is for another linear mixture value, another alpha. And these two curves basically show the mean error across different alpha values to show that no matter what linear mixture constant you take, adaptive damping factor always does a lot better than constant damping. And with that, we move to the last chapter, location-aware image understanding, and we use that for business recognition. The paper was published in ACM Multimedia 2013. So far we talked about how we can geolocalize a video image or how we can refine it. We were mostly concerned about finding the location, but what if the geotag is given? How we can actually use it, and that brings us to location-aware image understanding. And that's, again, particularly very important because in the future, most of the images are going to be geotagged. So it's good that, to develop methods to actually use these geotags. So to show that, the geotags can actually be used for better understanding the content of the image, we are trying to do business recognition here. That means we are trying to identify the storefronts here. So we want to say this is Burger's Bagel, this is Nicholas Coffee, and this is Tavern, and with their address and user ratings, which are byproducts of recognizing the business. So our method is the block diagram is given an input image and the geotag. We go to business directories and we extract the over complete list of nearby business, which we call the business lexicon. We expect the right business to be among these. We do text processing on the image, and using the business lexicon also we do image matching, and we fuse the probabilities that each of these modalities gives us in a late fusion formulation, and in the end we take the business. So the text processing step is, given the query image, we do text detection. So each of the text detection gives us the patches of characters. So for each character using Gabor features, we'll nominate a set of possible characters that would be visible in that patch. And also we have the business lexicon. So we match the permutation of these form against the business lexicon, and we come up with a probability distribution for different businesses. So X is different businesses and Y is the probability. It shows what is the likelihood of each of those nearby businesses to be visible in the query image. So our novel multi-hypothesis character recognition, it actually works based on Gabor features. What it does is that given the query, we actually train the Gabor features using a set of like different variations, erosion and dilation using several fonts. And so we have the query patch using nearest neighbor on the Gabor features. We nominate a couple of different characters which could be possibly visible in the query patch, but we don't fix it to one because, again, it's the appearance of text in business storefronts is very complicated. Usually the first one is not the right one. And so they form a set of permutations. And we matched, and actually, by the way, the red circle shows the right character here. So these candidate characters form a set of nominations, and we match them against the business lexicon. So each of those businesses best match to one of these permutations that the query patch forms. And that actually is transformed then into a distance between the text in the query set, in the query image, and the business lexicon. And we transform it using sigmoid function to probability to be able to represent what businesses might be visible in terms of the textual information. However, many images do not have text. So, or the text is too complicated to be, or cluttered to be detected. But there are many relevant images in the web. So we use business lexicon as keywords and form a set of like 3 different keywords as business name plus the city that was captured is located at in a storefront, and we retrieve a set of images from the web for each of those businesses. For instance, for Primani Brothers, we retrieve these images from the web. And for Subway, another set of images. And if you look at actually the query image and compare them to the retrieved images, some of these images actually have similarity, have something in common with the query set, and they are marked with the red boundary. So we actually want to match the query image based on the image content against these retrieved images to be able to tell whether Primani Brothers, for instance, is really visible in the query image or not. So for that, we do matching using bag of visual words. And then again, we transform the distance between one query image, between the query image and the reference set using sigmoid function to form the probability. So in the end, we'll get one probability based on image matching for different businesses. And then we fuse the probabilities that we get from text processing and image matching in a late fusion step to be able to get the final business. And that business is the one which has the highest likelihood. So experiments were on images from San Francisco and Pittsburgh, and the ones which show no business were manually removed. And so single modal mode, 69% was achieved by just text processing, and 69% is the accuracy of business recognition. And image matching by itself does 49%, and fusion gives 75%. Also, in terms of text processing and text recognition, our method does better than the several baselines in terms of recognizing text in the storefronts, and this shows the precision recall curve for our method versus Wang et al. And this video shows the results for video. As you see, like the businesses that is shown in the video is overlaid. Its name is shown, like for instance, Cheesecake Factory, and its address and user rating and phone, which are like again byproducts of recognizing the business. So to summarize, we talked about geospatial analysis of ground level imagery in this dissertation. So we addressed 3 foremost and most fundamental questions in this area: how to find the geolocation, how to refine the geolocation, how to use the geolocation. And for image geolocalization, we talked about first local features, low-level feature correspondences, and geospatial pruning. Then we'll talk about multiple nearest neighbor feature matching using generalized graphs. And also we talked about geolocalizing videos using Bayesian filtering and MST-based reconstruction. Refinement of geolocation using random walks for the images which are already geolocalized or are coming with some geotag, but they are inaccurate, were discussed. And then finally we talked about location-aware identification of a store. So these are the papers that I presented, PAMI, CVPR, and ACM. And there are a couple of like CUPR, ICMO, and ECC. There are a few other papers like CUPR and ECC, but we didn't completely discuss in the dissertation, in the presentation. So for the future work, there are a few major things in this area that can be done. So cross-view matching is one major task. So ground level data is like a street view, crowdsourced images are available, but they are still not as, the coverage is not as good as, say, satellite imagery or bird's eye imagery. So it would be great if we had methods which could localize a ground level core image using satellite imagery. In principle, it should be possible, but it's very difficult. There has been some work, but still very preliminary. And the biggest problem in this area is identification of reliable point correspondences. Incorporating semantic information in geospatial analysis, text, mid-level features, facades, and so on. Right now, none of them mostly are used. They are mostly ignored. Most of the localization methods based on establishing low-level correspondences, which are actually have its own disadvantages. Also, we have GIS. We pretty much know where everything is. We know where ATMs are, subway stations, bus stops. So we could basically incorporate that into geolocalization or geospatial analysis, which is not happening right now. So for video geolocalization in the wild, we did one of the first works in this area, but a lot is left to be done. And that's reflected actually in practice that, like, say, services for images like Panoramio, Google Earth has been around for a while, but nothing for videos has been there. So you can't, there's no service that you can go to one particular location and say, show me the videos of this location. There's nothing like that, but there are many similar things for images. And also in the end, more location-aware frameworks, obviously. In the future, again, most of the images are going to be geolocated, so we better use this. And so this could be either for enhancing traditional computer vision tasks or attempting new ones. For instance, like for scene parsing and scene understanding. Given where this image was taken, should be able to help you to better understand this. Like it could give you the outline of buildings, or could help you with getting priors about the perspective of the scene and so on. Also, like detecting objects, like knowing where you are, assuming that you have priors about objects, you should be able to detect objects better. But none of this is actually happening right now. And thank you.